Moving on to Tobias Brunner, we've already heard about the different variants of hydrogen that can be refueled. For those of you not so familiar with it, there's gaseous hydrogen, there's liquid hydrogen, and there are a few things in between SLH2, supercooled liquid, or cryocompressed hydrogen. And Tobias Brunner will lead us through the technology as well as through the advantages of cryocompressed hydrogen. I'll be brief on your CV because if I'm extensive, the time is up. Tobias Brunner is Managing Director of Cryomotive, which is working on cryocompressed hydrogen. He's also Managing Director of the company iNergy, which is in the engineering space. He is one of the key drivers of hydrogen development here in Bavaria, being the driving force behind the local Highland project in Landshut. We've just inaugurated an electrolyzer in the important village of Pfeffenhausen, which will supply hydrogen to the Bavarian Hydrogen Project and also to the Hydrogen Technology and Application Center, where we have the pleasure to cooperate with Tobias and other partners, funded by the German Ministry of Transport and the Bavarian government. So that there is a lot going on apart from your Cryomotive activities, but still this will be the focus of your presentation today. For the sake of time, Tobias, please take over. And sorry for shifting you behind Dirk. I think there was a technical issue with the presentation mode, but now it should be all set.
Thank you, Uwe, for the introduction. Yes, we're all set with a technical part. I definitely would like to share if that's possible. So I don't have the right to share. Is that possible? So let me share my screen.
That should have already been done.
Fair. So let me see now. Great, thanks. I will share. Good. So yeah, thank you for introducing me, Uwe. So there's a lot of projects ongoing same time, and it's hydrogen time. That's for sure true. We need green hydrogen for various matters and sectors in Germany and worldwide. I have the pleasure to introduce you to cryogas, cryocompressed hydrogen gas. I fully agree with Paul Karzel. I also agree with Dirk Rast that basically for now we have gaseous hydrogen, and then the next few years will be dominated by 350 bar gaseous hydrogen refueling because it's available and it's affordable. But the future of long-haul trucking may also lead to larger stations with 3, 4, 6, and 10 tons of hydrogen potentially. And their delivery of hydrogen to such stations is a big challenge, and that's when liquid hydrogen might come into play. And cryogas may play a role into that because it is a very robust technology to use the high density of liquid hydrogen or of cryocooled gas to store 1,000 kilometers of range on board such long-haul trucks. Also, the station can be quite of modest cost, very compact, and very quick in refueling. So a 10-minute fill for 1,000 kilometer range is doable. And in the future, there is a way to also change distribution with cryogas. So you could basically store cryogas on a trailer and double the amount of capacity of such a trailer by distributing a cold gas. So that's the fields that Cryomotive works on with the cryogas technology. So what is a cryogas? It's a compressed gaseous hydrogen at cryogenic temperatures up to 40 MPa. If you look at the thermodynamics, then you can see that the so-called compressed gaseous hydrogen 350 bar or 700 bar plays into minus 40 to plus 85 temperature range. You have liquid hydrogen that plays below 33 Kelvin usually. And then there's a big range of cold gas, which we call cryogas. And in that range, we operate a cryogas storage. It's an insulated pressure vessel that we fill with cryogenic compressed gas that can be for example, generated from liquid hydrogen with a so-called cryopump. I will give you a few details in a minute. And the range of operation is between 15 bars and 450 bars, and temperature-wise, 120 Kelvin and 30 Kelvin. Why do we do that? Because the density is much, much higher than 700 bar. So we can go up to 76 grams per liter usable density on board a truck with that technology at 400 bars. So we can basically use less material, less package space to store more hydrogen, similar to liquid hydrogen in terms of densities. So what are the opportunities on board? We can store 10 to 100 kilograms per vessel with a gravimetric density of 8 to 10%, weight percent, and volumetrically, this is a very effective technology. Usually the measure is kilowatt hours per liter system. 1.2 to 1.5 is really very high. We can actually simplify insulation compared to liquid hydrogen. We can allow more heat leak because we have a robust cryogenic gas that can absorb more heat, and it will not lead to high blow-off rates. We can actually provide holding times of days, and the emptier the system is, the longer you can park. Basically, it's a compressed gas storage that can store 350 bar ambient temperature gas and can be overfilled with a cryogenic gas. We have quite a freedom to package because we are gaseous. So basically, we're not so sensitive to heat leak. We can distribute multiple tanks over truck in these various configurations. And the 2-tank system along the frame, left and right, can lead us to 78 kilograms usable hydrogen. If you package more of these vessels, it can be more. Refueling is what we believe the biggest advantage of the technology, because we basically are compliant to both liquid hydrogen delivery as well as gaseous delivery, because this is a gas tank, so we can fill 350 bar ambient temperature gas. We can also cryocool such a gas with a new device that we are currently developing. We call it a cryocooler, and that would bring us to densities of 70 to 80 grams per liter. So we triple the density of 350 bar gas by cryocooling the gas, and it is less energy consuming than liquefaction. However, if liquid hydrogen is available, that's the best way to do it. So you deliver liquid hydrogen with up to 4 tons to a station, and then you have a so-called cryopump at 500 kilograms per hour that can directly fill from such a liquid storage into the truck at densities between 75 to 85 grams per liter. A third potential way of the future would be to cryocool a gas at an electrolyzer. So we're building an electrolyzer, and we may also have a cryocooler there in the future. With 2 to 4 kilowatt hours per kilogram cryocooling effort, we can produce a 40 MPa 400 bar gas between 50 and 80 Kelvin, which has a very high density above 70 grams per liter. That can be distributed to the station, and at the station you need a moderate energy to then fill such a gas. It could also be heated up, and you have a 350 bar refueling. Why do we see that technology so interesting? Because the first generation that had been developed at BMW used a submerged piston pump for providing the cryocompressed gas. We see another opportunity now that's much more interesting cost-wise. It's the insulated reciprocating pump skids that you see in Walmarts in the US already, where they all have liquid hydrogen delivery because they consume so much, and liquid hydrogen is available there, and it's very effective in terms of energy, power, and especially cost. So such a reciprocating piston pump will actually cost less than 250,000 euros for a 500 kilogram per hour pump. So we have these offers on the table. We are currently planning to modify such a pump for cryogas use. So it's a really cheap and simple way to refuel hydrogen. We are developing a new nozzle that is very high performant, 15 kilograms per minute, 250 grams per second for 40 MPa. And you see this is quite a compact refueling nozzle. Another advantage is a very high density cryogenic gas that doesn't need the same insulation as liquid hydrogen, and with that is more robust, and this reflects into the nozzle and receptacle system that you see here. So how would such a station look like? Basically, we have a liquid tank. We have the reciprocating cryopump skid, 500 kilograms per hour. It directly goes to the dispenser, and it can fill up to 500 kilograms per hour. At 40 MPa, such a station can easily be done for 3 tons per day with a footprint of less than 300 square meters and an energy consumption of 0.5 to 0.75 kilowatt hours per kilogram. There is no high pressure buffers needed, no heat exchangers needed, no communication between the station and the vehicle needed, and you have unlimited back-to-back refuelings, a direct feed from the cryo pump into the vehicle. So it's more or less a diesel-like way to refuel. You can do that for larger stations. Just you add a dispenser, another cryo pump, and you can basically do double the capacity per day. I think cost-wise, as I said, these pumps are quite affordable. So it is, according to my experience, one of the lowest cost station configurations available. And that's what you see here again. So we see that we can be extremely cost effective in terms of station, the total cost of ownership of the station. If you deliver compressed gas to a station and you need to provide high mass flow rates with a lot of high pressure buffers with the pre-cooling system and so on, you end up with much higher cost. Yeah. To finish and conclude my presentation, we're very proud that we are now winding cryogenic compressed pressure vessels in Bavaria. The first ones you can see here. And yes, we're going to do it. This is the full truck size of 2 meter and 40 in the diameter of around 700 millimeters once it's insulated. So that's the first time I think that these cryogenic pressure vessels Type 3 are manufactured in Germany, and wish us the best luck. I think it's an interesting opportunity for long-haul trucking in the future. Thank you very much.
Thank you so much, Tobias, for the comprehensive and fast overview. I hope everybody could catch up in time. A quick question from my side, leading on to something that Jürgen Goldner from BMW also commented on. He said, on the technology side, battery versus fuel cell, it's complementary, not a competition. How do you view it on the refueling side? I mean, is cryocompressed a complement to gaseous or liquid hydrogen refueling? Is it a competition? How do you see things positioned going forward?
Yeah, I think one of the advantages is that we are quite synergetic to 350 bar. So we can basically fill 350 bar at any 350 bar gas station. It's a 450 bar tank, and then you can fill it with up to 438 bars. That's the common 350 bar refueling. Once the throughput of such a station increases, I think liquid delivery becomes an interesting option. And once you have liquid delivery to such a station, then you would switch from the gaseous compressors to these reciprocating pump skids that are very affordable. And then you can produce a gas at 450 bars, 400 bars, even up to 500 bars if you wish. And you can either heat it up or directly fill it as a cold gas. So this is very synergetic to 350 bar stations. And that's why we believe cryogas can be an amendment to an existing infrastructure. For sure, if we have liquid hydrogen available, we can do it that way. If we are only having gaseous, you can either fill gas or cryo-cool the gas or have cryo-cooled gas delivered to the stations. So there's various options here that give interesting new opportunities, because I believe the next 5 years will be dominated by 350 bar gas. I agree with everyone mentioning that. But I also need to say that green hydrogen production in the next 3 to 8 years probably is very much in Germany. We are not seeing import in a large manner. And with that, cryo-cooling a gas is a near-term option to also increase density for long-haul trucking.
Thank you.